So I'm going to take a few minutes and I'm just going to take a lesson. We're going to talk about tension on ropes or tension in cables. This is a section that takes all of what you've done on forces and it's going to relate it to the rigging that you do, which I think you'll find quite practical. And I think you're going to find that some of it's going to give you the reason for the numbers that Andy gives you when you get talking about rigging and doing lifts. Okay, so this section shouldn't be too long. I had done it up once before, and some of the examples were unnecessarily complicated. So I've gone back, I've edited it, made it so it's more realistic for what you need to know, especially given the fact that we don't have the in-class discussion that we usually do. And hopefully that will give you the information in a way that is easily understood by you. We're going to look at, as soon as you get back after break, we're going to look at energy and work. So we're just going to take a single class and look at that. It relates to forces very easily. And then you'll be in for an assessment just before you head out for your OJT. If you're going for OJT, I'm not sure exactly how that's working this year, but I will have those posted early next week, just so that if you are wanting to use what's called Reading Week for reading and you want to get ahead, you will be able to. So I should have those available for you shortly. So with that said, let's jump into this section, and calculations should be pretty easy. So, oops, I've taken this section from climbing because doing a rescue and climbing, there's a lot of similarities involved. So this was a great graphic from, I borrowed it from the internet. It's trigonometric analysis of the tension in a climbing anchor. So let's say you have somebody climbing, they've got an anchor set up and the load or the individual is down below. So you've got an anchor set to 2 points, so set to 2 points on a rock, and the individual suspended below. When that occurs, the load, so this is the individual at the bottom, is equally shared between the two anchors. That's assuming the angle is symmetrical. And we're always going to assume the angle. We're often going to assume, I shouldn't say always, I'll often assume that angle is symmetrical for you. And what they mean when they say the load is going to be shared equally is we're going to find the forces upward from the cable that's pulling up will have to match the force downward on the load. And then you'll find these outward forces. And we know that there's tension outwards here, out to the anchors. So not only because the force pulls at an angle, there's an upward force, but there's also an outward force. Those two outward forces, we're going to find that they balance, okay? So I'm not going to come back exactly to this diagram, but you may find it's helpful to come back to this diagram later when we get to examples that have this angle in between, and you're looking at how much tension is on the cables, what's the force. I thought this was just a great schematic for you to be able to use. Now we're going to start simple. And the first thing we're going to start with is a definition. So if an object is at rest, it's considered in static and it's in static equilibrium, all the forces on the object are balanced. So that's just going back to Newton's first law, which we've covered. So if something's at rest, if it's not moving, all the forces are balanced. At the very end of the lesson, we'll say, well, what if it is accelerating? So for all of our scenarios, we're going to look at the net force being equal to 0, and that's going to be a key component for solving these questions. I'm going to get rid of this little video because it's in the way. So I'm going to actually start with some calculations. We'll give you some examples. And as I give you the examples, we'll give you kind of how get the theory. So we've got 3 different setups, 3 different masses. We've got mass 1, mass 2, and mass 3. You can see they're hanging at different angles, but they all have the same tension in the rope. You'll see there's 50 newtons of tension here, 50 newtons, 50 newtons. What we don't know is the tension from the hand, and we also don't know the mass of the object. So in this question, we want to find out which mass is the heaviest. So this actually simplifies some of the calculations for us because we only have to consider one angle. So for the very first question, it should be nice and easy. That's one that I shouldn't have to tell you. anything about in order to calculate. So for the very first one, we know that the tension of the rope is going to be equal to the force of gravity. Call this T. So for the very first one, tension equals Fg, which means the force of gravity is equal to 50 newtons. Well, you can use that to find your mass. So 50 newtons is equal to mass times 9.81, dividing both sides by gravity. Our mass is equal to 5.1 kgs. So this is a 5.1 kg object. All right. Now let's look at the next one. And this actually, we can relate this quite nicely to rigging once we finish the question. You'll see where it makes a really natural hypothesis. So for the next one, we want to find out what the mass of the object is, but this time we have an angle. Now, if we think about vectors, some of the tension on this rope is holding the mass up. We'll call that Ty. Some of the tension on the rope is counteracting the hand, and we'll call that Tx. Okay, so we've got Tx and we have Ty. We want to find out, so we also know that this tension X should be equal to the force applied. It's supposed to be an A, if these are balanced, and we also have Fg. And Fg and Ty should be equal to each other. So the first thing we're going to do is let's break this vector, break the tension in the rope. So this is our main tension. Let's break our tension in our hanging cable into two components. So tension Y. So we know this is our hypotenuse. We've got 30 degrees. Y is adjacent to 30, so it's going to use cosine. You can draw your triangle out, use your trig if you're not sure. So tension on the Y is equal to 50 newtons times the cosine of 30, which is equal to 43 newtons. Tx is going to be basically the same, but we're going to use sine. So 50 times sine of 30, we get 25 newtons. So let's find out, first of all, I guess we can say that the tension from the hand, so the force applied by the hand, is equal to tension X, which is equal to 25 newtons. If we look at Ty equals Tx. So tension in the Y direction. I said Ty equals Tx, I meant Ty equals Fg. Equals the mass of gravity, which is equal to 43 newtons. Now we can find our mass. So 43 is equal to mass times 9.81. So our mass is equal to 43 divided by 9.81, which gives us 4.4 kgs. So there's our key information. So we know this force is 25 newtons, and this force is 4.4 newtons. All right. And what about the next one? So in this example, we're just changing our angle, and the angle has changed this time to 60 degrees, so exactly the same calculation. Our tension in the Y direction is going to be 50 times cosine of 60, which will leave us, because 30 and 60 go together to give us 90, we're going to find we get the opposite values. 25 newtons. Tx is going to be 50 sine 60, which gives us 43 newtons. And then the force applied is equal to the x direction, which is 43 newtons. And force of gravity is going to be equal to 25 newtons. And then we're going to find that the mass is equal to the force of gravity divided by 9.81, which is equal to 2.5 kgs. So if you take a look, and I'll put the numbers in here just so we have them. So if you take a look at each of these, if the tension, let's say the maximum tension that can be supported by this particular rope or string is 50 newtons, if it's hanging perfectly vertical, it can support more mass than if we are at an angle. You'll notice as the angle increases, the amount of mass we're able to support by the cable decreases. Okay, so if the tension in the rope stays the same, the hand is just balancing it, keeping it from moving. The tension in the rope stays the same, we can't support as much mass at higher angles. Now, I don't know how much theory you've done with rigging so far, but you're going to find the greater the angle we have between like two cables in a configuration that's like a triangle, the greater the angle, generally speaking, the more negative effects we have, because what happens is you can't lift as much base, and you can lift less mass with the same cable because the load is reduced. Now we're going to look at that at the very end if that sounds a little bit confusing to you. The other thing that's often said is when somebody's lifting with a crane, they're not to do lifts at an angle. Why wouldn't they do lifts at an angle? Well, if this was all the same mass and we did a lift at an angle, we would find, well, from the first mass to the last mass 1 to mass 3, we're able to, as the angle increases from 0 to 60, we're able to support only half of the weight. So if you were doing a lift on a heavy object, if you were lifting at an angle, especially a 60-degree angle like we have here, you would have it would double the tension that's in the cable. So that's one of those things that you get a little bit of as you think about lifting objects. We'll look at several practical examples of where that comes in. Now, before we move on to some other questions, we're going to do one more simple one, and then we're going to go into rigging. This question might not look as easy as it is. So if the forces on this 35 kg mass are in equilibrium and the angle is 40 degrees, what's the tension in each cable? So we have a 35 kg object, and the angle here is 40 degrees. So this is something that's been suspended. Oftentimes in a physics class, they would say this is a sine, and they would know, okay, what's tension 1 and what's tension 2? The key to solving this is to think about what equilibrium means. So it's not moving, it's stationary. So all of our forces are balanced. So the first thing we do is we find the force of gravity, which is 35 times 9.81. 35 kgs times 9.81 meters per second squared leaves us with 343 newtons. If that is the downward pull from gravity, there must be a supporting upward force of 343 newtons. Now, all of the upward force is given to us by tension 1 or cable 1. So we now know that the upward force that this cable supports is 343 newtons, and that's at 40 degrees, so we can actually calculate what is tension 1. So just think about your triangle map. So this is opposite. So the sine of 40 is equal to the opposite side, 343 newtons, divided by, this would be our hypotenuse, tension 1. So tension 1 is equal to 343 divided by the sine of 40, which is equal to, I calculated that here, 530, I think it's a 533. Bad when you can't read your own writing. I'm sure that's a 3, not an 8. 533 newtons. Okay, so we've just figured out 1. Well, how do we go about calculating tension 2? Well, we know as much as there's an upward supporting force from tension 1 also has a horizontal component to it as well. And the horizontal component of tension 1 must be equal to the tension in row 2. So what we need to now find out is what is, let's call this T1X. Okay, it's horizontal. So let's find out what is T1X. Well, it's the adjacent side, so we would use cosine. So the cosine of 40 degrees is equal to 343. Let's change that. It's not supposed to be divide. And you could do this with cosine. You could also do it with tan. There's a couple ways you could go about it. So if you want to try and figure out how you do it with tan, you can. Cosine is going to use my hypotenuse, so off adjacent side T1x divided by the hypotenuse, which is 533. Okay, so T1x equals 533 times the cosine of 40, which is equal to 408 newtons. So the tension in T1x is equal to the tension in 2 because the horizontal component of tension 1 balances out tension 2, which is all horizontal. So this is 408 newtons. So not overly difficult, just some simple trigonometry. Okay, hopefully you remember your trig from last semester. We've done a little bit of it as we've been going, but these ones kind of make you stop and think about trig without necessarily just memorizing what's sine and what's cosine. Now let's look at example 3. Now this gets us a little more like you would have with rigging. Now oftentimes with rigging, we maybe would flip this picture upside down. So you have 2 anchor points, and then this is your lift point. And I do have a graphic with that, I think. Trying to think of how many slides ahead. Yes, I do have a graphic with that in here. But the math is going to be exactly the same whether we flip this upside down or not. So in this case, a suspended object, so this is like the very first slide where I just first started talking about how the vectors work. If a suspended object has a mass of 120 pounds, what's the tension in the cables if it is suspended with equal angles measuring 25 degrees? Now, the first thing for this question that should hopefully jump out to you is the word pounds. You haven't had pounds in a question yet. We need to convert that to kgs. So 120 pounds divided by 2.2 leaves us with 55 kgs. Okay. Which means our force of gravity is equal to 55 times 9.81, which leaves us a force of gravity equal to 540 newtons. And that's just rounded to a whole number rounds to 540. Okay. Now it tells us the angles each measure 25 degrees. So you've got that in there. If the angles are the same, the upwards tension in each cable, and I'm going to draw it just draw them kind of separate from each other. I'll call this one T1 and I'll call this one T2. So T2, T1Y, T2Y need to be equal to each other. They're also supporting 100% of the force of gravity, which means that if we take the force of gravity and divide it by 2, we're going to get T1Y or T2Y, whichever way you want to look at that. We could just call, because they're the same, you could just call it TY. You just have to remember that there's 2 cables, so it's each strand supports half of the vertical weight. So T1Y is equal to 540 over 2, which gives us 270 newtons. Now we want to know what's the tension in the cable. Tension in the cable is easy to solve. So we've got opposite, so that goes with sine, and hypotenuse. So the sine of 25 is equal to 270 over tension 2, which means tension 2 is equal to, flipping places, 270 over the sine of 25, which gives us a tension of 638 newtons for each cable. Okay. Now this is a lift angle, which you wouldn't want, usually it's a lift angle that would be avoided. Lift angles in this range up here, so this is our rigging, let me just double check. What's the horizontal angle is what it's referred to. This horizontal angle, that's this angle here, or the included angle down here. Those are two terms that are used. So the horizontal angle here, 25 degrees, usually you don't want to be less than 30 degrees if you're doing a rig. Why would you not want to lift something when it's at 30 degrees or below 30 degrees? Well, we'll look at that shortly, but just think about how the tension in each cable, how it compares to the force of gravity. Normally, if we're supporting with two cables, we want to reduce the tension. We're using two cables to make it easier to lift. So we'd want to reduce the amount of tension in the cables to basically equally or as equally as possible support the weight. Look at how that tension compares to the weight. And we'll look shortly at what happens. Well, what if we have a larger angle up here and things are a little more vertical? We'll see what happens with that in the next example. So in this example, I have exactly the same object. So there's a few calculations that we don't have to do. One of the calculations I'm not going to do again is I'm not going to figure out the force of gravity. Force of gravity is 540 newtons. It's the same weight of object, it's the same mass of object, so it's the same weight of object. But this time what we've done is we said, well, what if these angles are 55 degrees and 25 instead of 25 degrees? And I'm sorry the sketches aren't to scale. We had so much I was working with. Okay, so we've increased this angle. Actually, this is getting really close to the ideal lift angle of 60 degrees. So what's the tension in the cable? So we know if we can figure out what's the vertical tension, if I can figure out what is Ty, we can figure out the tension in one of the cables. So Ty is going to be equal to half of the force of gravity, which is equal to 270 newtons. Now we can find out tension. So what the tension is in just one cable. So this one uses opposite, which is sine, and hypotenuse. I'm going to actually write it out. And maybe it's just me. I like to write it out unrearranged and then rearrange it. And as many times as I do it, I still prefer to do it that way. So the sine of 55 is equal to 270 over t. I guess the reason why I like to write out this form first is it confirms in my mind whether it's a multiply or divide scenario. And I'm one of these visual people, I need to actually see it, which gives us 330 newtons of force in the cable. So let's just compare that with when we had a 25-degree angle. At 25 degrees, we had 638 newtons of tension. So if you think about tension on the rope, what it's going to do in terms of strength, you're going to have a much stronger cable, as opposed to at 55 degrees, we have roughly half the tension that we do when we have 25 degrees. So that's one of the reasons why these angles are really important. This angle, you want to keep this angle between 30 and 60, but ideally you keep it as close to 60 as possible, because what that means is that cable is supporting a lot less than the mass of the object. So it's going to have less stress on the material. Okay, now sling, so that's your sling angle, 55. Now in this included angle in here, we typically want to keep this angle less than 90 degrees. When you're doing a lift, and the reason you want it less than 90 degrees is because if it's over 90 degrees, it means you're going to be supporting close to each cable has to be able to support almost double the weight of the object. Whereas if we're less than 90 degrees, like in this case, which we'd have an included angle of 70 degrees because it's less than 90, it keeps less tension on the cable. So just some of those little things that are, I guess, practical for why we lift the way we do. Now here, I want to think and apply. As the sling angle decreases, what would be some issues that would cause concern? And a sling angle of 60 degrees is ideal. How would physics justify this? Well, the 60-degree angle being ideal, I guess I kind of gave the answer for this already, but that's because it puts roughly half of the it allows for substantially less tension in the cables as compared to when you have larger angles. Now, as these angles decrease, we get more and more tension. And one of the issues we have here, see how this vector would be very small? So you have less weight supported vertically, but we have a lot of force pulling in towards the center. But these forces just cancel each other out. Basically, they put strain on the system that does no work, that doesn't actually affect anything. It doesn't support the object. They're just competing forces. And if you have, depending on what type of material you have in this scenario, if it's something that could bend or buckle, you'd want to make sure you're using a high strength spreader in this case to keep these apart, because what can happen is that force is pulling towards each other. They cancel each other out, but because they're pulling towards each other, if the object that we're fastened to can't support those two forces, it could crumple in between. Or if the cables that you're attached to, if it's something that is tied rather than secured to fixed rings, we could potentially have slip happen because there's more force pulling towards the middle. Or if we think of these as rings attached to a material, we're putting more stress on the material than we are in this scenario because there's less of that, I'll call it a useless inward pull that just keeps the two rings away from each other. Okay. Now you might ask, well, why don't you just use two perfectly vertical cables? Well, sometimes that's not possible. So anyway, just one of those kind of practical examples. I've got a really good chart here at the very end that gives you a nice example of the angles. Well, I guess I took out one example that I meant to leave in. Oh well. So this chart is a chart. This reduction factor is the weight reduction factor. So this is the factor if you're pulling something at a 90-degree angle, so perfectly straight up, 100% of the weight is going to be transferred to the vertical, transferred to the cables. So that's assuming we're doing a lift with a cable like this. Okay. As you change this angle from horizontal, as this angle decreases, by the time we get to a 30-degree angle, you're only able to lift half of the weight that cable would be rated for, and the tension in the cable is double what it would be if you were lifting at a 90-degree angle. So it's all looking at these kind of tension, weight factor to tension factor. You notice you get a really big difference between them as the angles decrease, as this angle gets smaller. So whenever you're lifting, you want to keep things your base, you want to keep your angles at horizontal quite wide. You don't want to have your angles like so, because it puts substantial, way more tension on your cable, which is completely unnecessary. and you're just not, you have undue stress that you don't need to have. And one final question before this section finishes. If an object goes from rest on the ground to moving upwards as a crane lifts it, how will the tension in the cables supporting the object be affected during the initial few seconds as it accelerates? So this applies regardless. So in this case, we're just doing a perfectly vertical lift. Now we're going to deal with pulleys shortly. And I know you've dealt with pulleys with Andy. I know you would have looked at Mechanical Advantage with him. But this one, we're doing lifting, basically perfectly horizontal. We don't have one of those funky slings, but we don't have to really worry about that. I want to think about the tension in these cables. Is it going to be larger or smaller as this particular blade is lifted from rest on the ground to moving upwards? Would a crane want to keep the part accelerating, or will it want to follow a constant velocity? The key to this question lies in at rest or constant velocity. So at rest or constant velocity, the net force is equal to 0. So tension has to be equal to the force of gravity. We've used that principle for the last examples. If it's going from rest to a velocity, it has to speed up at some point, so it must accelerate. Okay, so it has to accelerate to start moving, which means F net equals mass times acceleration, and it is going to be greater than 0. So it's going to be bigger than 0, which means our tension now has to be bigger than the force of gravity because the tension is what's pulling it upwards. So during the first few seconds when something begins to lift, there is always going to be more tension in the cable than once it starts moving at a constant velocity, because for the lift to start occurring, tension must be greater than gravity or the object wouldn't start to lift. Why do you think? There are specified, you can't max out the weight that can be supported by a cable. Why do you think there are safety parameters that cables can usually hold? They're rated for, they're always rated for slightly more weight. They're always able to support slightly more weight than what they're rated for. Put it that way. I think I said that straight. And why is that? Well, it's a safety feature. If they were only able to support exactly the weight that they're rated for, as soon as you went to lift something up, they would snap. Because at that second, you have acceleration, which means there's more tension. So they always rate them for a little bit more. And then you have a parameter that you wouldn't want to overload your cable so that you have room for that acceleration to occur. So that just gives you some kind of think and apply practical examples of forces. And that finishes off the entire force section, with the exception of talking very shortly. There's only a couple examples of how work works. Once you know how forces go, work is one simple equation that's easier than calculating, just as easy as calculating the force of